Hi, everyone. This is Don Baskin. Last week's lecture on structural optimization and lightweighting was unfortunately not recorded, so I am redoing the lecture now, so you guys will have this to listen to. So, because of that, I will start right now. So let me share my screen. Okay, so we'll start here. This is the third lecture. Every lecture will begin with this message. Structural efficiency and lightweighting requires both geometry and materials in order to get the most efficient solution. That will start every lecture with that message. Otherwise, we'll start the lecture here. Here you see two bicycle frames. On the left is a mid-70s Colnago from Italy. This bike is made out of chrome moly steel. The tubes are brazed together using brass. The ultimate tensile strength of the material from which the frame is made is about 800 megapascals, and the minimum wall thickness up here in the top tube is about 0.6 millimeters or 600 microns. This frame weighs about 2 kilograms, the frame and fork. On the right here is a Cinelli, also made in Italy, bicycle frame. This is a very modern frame. It's believe they made it this year, so it's a 2020. And in this frame, they use a more interesting or more exotic steel than they do in the Colnago. They put a lot of niobium, relatively speaking, in the steel to refine the grain size. And this is, if you recall, this is one of the strengthening mechanisms we spoke about in the last lecture. And through putting in this niobium, as well as some chrome, moly, manganese, and nickel, you're able to produce a steel that has a much higher ultimate tensile strength at about 1250 megapascals or 1.25 gigapascals. In this case, the tubes are welded together using TIG, so tungsten arc welding. And in the top tube here, at the midpoint, the minimum wall thickness is 350 microns or 0.35 millimeters. And overall, this frame weighs, including the fork, weighs about 1.6 kilograms. So in going through these 45 odd years, the bicycle industry, even using steel, has been able to dramatically reduce the weight of these bicycle frames by using materials and geometry. So the materials modification here is the higher strength steel. And also by looking at these two frames, you can see that the diameter of the tubing in the white frame, the Cinelli, is actually much bigger than the green Colnago frame. And so that's the geometry side of this. And we're going to, this effective geometry is going to be the focus of this lecture. The main modes of loading are tensile, compression, shear, bending, torsion, and buckling. Tensile, compression, shear. So tensile loading is, you guys pretty much all know what that is. That's if you have like a wire, for example, that's under a tensile load, for example, like a wire on a bridge, a suspension bridge. Compression is when you push the column together, try to get the ends to get closer. This is like a column that would be supporting a bridge, for example. There's shear, which I can think of some examples of the way suspension components are fastened to the frame of your car. And that's single shear. And there's also double shear. So double shear, as you can see here, means you've got the load is sort of applied in three different places. Sometimes this is called three-point bending. And this is a much better way to design parts. And when you start designing structures, it's always better to put things in double shear. Then there's a bending load, and you can think of like three-point bending like you see here. It can also be thought of as shear, I guess, except that I guess the supports are further apart. And then cantilever. Next is a torsion load, okay, and torsion is, for example, like there's torsion springs where things are loaded in torsion. There's, I guess there's some car suspensions that used to, instead of using coil springs, they use torsion springs. And the final mode of buckling we'll consider here, or final mode of loading we'll consider here is buckling. And this is similar to compression, except that in buckling, a lot of times you have a much thinner, narrower tube or beam, and you end up with, through loading it and compression, you can end up with a local instability, which then results in a compression failure or buckling failure. So it is slightly different than just compressive loading. If you consider the stress distribution in these different modes of loading, you'll see they're very different. So in tensile, if you have this beam here, this blue beam in tensile with load P, the stress is the load divided by the area. That gives you stress, okay? And in this case, if you could plot the stress across this beam of thickness H, you would see that the stress is the same everywhere along that beam. It has a linear distribution across the beam. Bending is very different. When you put a beam in bending, you have maximum stress at the outer skins of the beam, and you have zero stress at the center of the beam, the centroid of the beam. The equation for stress in a beam is shown here, and it's 12 times the moment, m, times the c, which is the distance from the center line, times b, which I'm calling the thickness into the page, and then h, which is the thickness you see here on the page. You can see here from this equation that the stress goes inversely proportional with that h to the third power. So what this means is that for a small increase in h, you can dramatically reduce the stress. And this is a very important effect, and you'll see in a couple minutes that this is something that can be used to reduce weight. If you had a beam in torsion, it's similar to bending. The stress at the neutral fiber and the centroid fiber at the center of this beam in torsion is 0. And then the stress is maximum as you go out towards the outer skin of this beam that's in torsion load. In fact, the stress tau, shear stress, goes with the inverse of the radius to the fourth power. So again, what this means is that if you increase the radius of this beam in torsion, the stress goes down very rapidly, very rapidly. If you decrease the diameter, decrease R, then the stress goes up very rapidly at that outer beam, that outer portion of the outside radius. So to give you an idea of what that might look like, here is a cross-section of a round cylindrical beam under torsion loading. The radius of the outer, the blue one here, let's just call it R. Then if we half the radius, we call that the green circle here. And then if we half it again, we call it the yellow circle. The stress in the outer part, the outer skin, can be represented by this vector right here. The magnitude of this vector, as you can see, would be very small. So that would be the stress under some load m, some torsion load tau, or t. Now, as you go to half that radius, the stress increases dramatically, and the length of that increase in stress would be represented by this vector here. And you can see it's definitely larger than this little tiny one here where I've zoomed in. Now for the really small diameter beam in torsion, where the radiuses are over 4, you can see that the stress, the magnitude of the stress is represented by this yellow vector here, all the way out here. So you can see that this effect of reducing or of increasing the diameter or the radius of this beam in torsion dramatically increases the stress in the outer fiber very quickly. Again, if you wanted to design a lightweight structure, you can very quickly reduce the stress by going to a much bigger radius. And I'll show you how that works in a minute. So here's another interesting example. Here are two tubes, tube 1 and tube 2. Okay, tube 1 has these are tubes, they have some wall thickness T. Tube 1 has a smaller diameter, smaller radius than tube 2. They're both the same length, L, and they're subject to moment M. The outer radius of tube 2 is 1.4 times that of tube 1, to give you some idea. Go to the next slide here. Given the same moment of bending M, the stiffness of tube 1 could be equal to the stiffness of tube 2, okay? But because the stress is reduced at the outer skin, because you've made the radius bigger, you can thin out the wall and still have the same stress. Okay, so the material is stressed to the same extent in tube 1 as tube 2, but because the wall is so much thinner, you can actually reduce the weight. So the weight of tube 2 is about 2/3 the weight of tube 1. And if we go back to our example here of the bicycle frames, you can see here, this is exactly what they've done here. They've gone to much bigger diameter tubes and thinned out the wall dramatically and achieved a real-world reduction in weight. So this is real-world weight savings using this principle right here. For the different modes of loading under different regimes, okay, so designed for strength or designed for stiffness, it's possible to derive constitutive laws that calculate the mass savings as a function of density and yield strength, or density and stiffness, for those different materials. So material 2 and material 1 having different densities, different yield strength, different Young's modules. These constitutive laws allow you to calculate the mass savings for different materials. So what's possible by switching to a different material. And for design purposes, these constitutive laws are grouped into mode of loading. So tensile compression shear is one mode, bending is another, and then I have one for buckling. I also have these tables for solid beams as well as tubes, so hollow beams. Here are the properties of 6 different materials. So there's density here, there's yield strength, there's Young's modulus, and Poisson's ratio. Starting at the top, this is a good carbon fiber with about a 70% volume fraction, so that's really, really high volume fraction actually for carbon fiber. The yield strength is about 1.5 gigapascals, and the density is about 1.6 grams per centimeter cubed. The Young's modulus is about 181. Okay, I picked these numbers out of a table. You can go into a book and you can find these values yourself. A medium or pretty high strength steel, but there's much higher strength steel, has a yield strength of about 0.9 gigapascals or 900 megapascals, a density which is actually pretty high of 7.86, a Young's modulus of 200. Magnesium has the lowest density, I think, of any structural material, even more than beryllium, at 1.77 grams per centimeter cubed. The yield strength is on the low side. It's only 159 megapascals, or 0.159 gigapascals. And the Young's modulus is also very low at 45 gigapascals. For aluminum, the data shown here is for a very common aluminum, 6061T6. Talked about that in the previous lecture on how to heat treat 6061T6. The density is 2.77. The strength is still pretty low at 241 megapascals. The Young's modulus is still very small compared to steel, 70 gigapascals. Fiberglass, like any composite, can have very different values depending on how much fiber you're able to incorporate together. But assuming an average fiberglass with a fiber volume fraction of about 45%, the density would be about 1.8, so about that of magnesium, so pretty low. The yield strength would be not too bad, about a gigapascal. The Young's modulus is actually very low because the glass fiber just isn't that stiff, and the epoxy matrix is not very stiff either, so it's only about 39 gigapascals. The final material on this chart is titanium. Titanium has a density roughly half that of steel, 4.42, actually less than half. I'm sorry, more than half, about 60%. So 4.42 grams per centimeter cubed. The yield strength is 780 megapascals, or sorry, 980 megapascals, so about a gigapascal. The Young's modulus is 105, a little tiny bit more than half that of steel. So that has very interesting implications. People usually think of titanium as a kind of whiz-bang material to make cars out of, or airplanes, or bicycles. But really, the Young's modulus, this Young's modulus, can hamper the performance of a structure made from titanium. The Young's modulus here is not changeable, really, not within a small percentage, or only within a small percentage. Young's modulus is intrinsic to a material. You can't really engineer around it. You might be able to alloy and change it by a couple percent, but for example, stainless steel and high-strength steel have the same Young's modulus within a couple percentage. Same with aluminum. You can go to a 7,000 series aluminum, and the Young's modulus is still going to be right around 70. However, the yield strength could be double or triple this for 7,000 series aluminum. Now, these values are chosen from a table. There's nothing special here. You can argue, that maybe these aren't right, and we can change them around and play with this. But just using these values for now. If you plug these values into the constitutive laws for weight savings for the different regimes and the different loading cases, the different modes of loading, so tensile compression, shear, bending, torsion, and buckling under the regimes of design for strength or design for stiffness, if you plug these numbers in the previous table into these equations, you can get the ranking of the potential to save weight in a structure relative to steel. And what's interesting here is that most people, think of steel as a old man's material or outdated. It's yesterday's news. It's rusts. They make bridges out of it, rusty bridges out of it. But really, steel has a lot to offer in terms of light weighting capability, and this is shown in the rankings here. So for the tensile compression shear loading under the design for strength regime, you can see that, yeah, you can get lighter with carbon fiber and fiberglass and titanium just under design for strength, okay, under those loading conditions. But actually, you can do better for steel than you can with magnesium and aluminum. You can actually, because the specific strength of steel is so high, you can design a lighter structure from steel than you can from magnesium or aluminum. So for an interesting example of this is some car parts that are designed for crash safety, where absolute strength is required and packaging space is limited. You can actually design a lighter structure from steel than you can from aluminum or magnesium. Design for stiffness is another place where under this mode of loading of tensile compression shear, you can design a lighter structure from steel than you can from these four materials: magnesium, aluminum, titanium, and fiberglass. Only really with carbon fiber can you design a material with a better, with a lower weight in a design for stiffness scenario under tension, compression, loading, tension, compression, or shear loading. As you can see here, okay, so you can actually get a 7% lighter structure out of steel than you could out of titanium for tension, compression, shear, and design for stiffness. The world changes dramatically when you have a structure that's under bending, because the weight savings potential goes with the square root of the yield strengths, as you see for design for strength, and the 1/3 power for the ratio of stiffnesses, or the ratio of Young's modulus in the design for stiffness scenario. All of a sudden, steel doesn't look so good. Okay, so assuming, well, okay, this is assuming you have enough packaging volume to make a bigger structure to package a magnesium or an aluminum part. But as you can see here, this is interesting rating. You could, in a design for strength, you could design a carbon fiber structure that was only 15% of the weight of steel. In using aluminum, you could design a structure that was 68% that of steel. Let's turn our attention now to design for stiffness. The stiffness of steel may be high, but because of the because of this ratio is in the third power, you could still design a stiffer, lighter structure in bending out of carbon fiber. The carbon fiber structure would be 21% of a steel structure. So there's very high potential there for weight savings. And that's why racing bicycles and airplanes and some racing cars are now made from carbon fiber, because the fibers themselves are incredibly stiff, and if you can get enough fiber packed into the epoxy, high volume fraction, then you can make a much stiffer structure at less weight, or an equivalently stiff structure at dramatically less weight. There's data in these 4 tables. So the second set of tables are for a hollow structural member. And I'm not going to sit here and go through all of these, but I would encourage you to go through these 4 tables and learn what is the real potential for mass savings with these different materials under the different modes of loading, under the different design regimes. It may even be more fun if you were to program these constitutive laws into Excel and then try doing this yourself. Create your own table and see what are the potential weight savings that you can achieve with these different materials under these different loading conditions. The results to these constitutive relations are shown graphically in what's called an Ashby diagram. So here are 2 examples of Ashby diagrams. These are, so in the design for strength regime, we have a graph that shows strength versus density, so specific strength. Okay, and these bubbles that you see here in sort of funny oblong or oval shapes are the region for these different materials. There are examples of these types of Ashby diagrams in Mr. Ashby's book, or Professor Ashby's book, I should say, and they zoom in so you can get a better idea of all these different materials and what the potential weight savings is for these different materials. Ashby defines the potential to save weight with this materials index called M. And depending, these M's change depending on whether you're designing for, or whatever mode of loading you're designing for, so tensional compression or bending or torsion. And then with the again with the regime, so designed for strength or designed for stiffness. And the way to minimize weight is to maximize this quantity. So for tension, compression, shear, in order to maximize M, you want to maximize the yield strength of the material and minimize the density. And for bending, you want to choose materials that have a high Young's modulus E and a low density rho. That's for tensional compression. You'll see that really these this approach is the exact same thing. It's the exact same thing that I've done up here. These are really the exact same equations, but they are for single materials rather than comparing 2 different materials. And they're, like I said, shown in a graphic way, which is actually very useful. It's a lot of fun to go through these different Ashby diagrams and look at all the potential for weight savings out of different materials. It really kind of cuts away all the reputation and hype around different materials and really seeing what's possible with materials, real materials. If you you might want to look up Ashby's book if you don't already have a copy, or maybe you can check one out from the library. Now we're going to switch gears a little bit, and we're going to talk about how to apply what we've learned in that previous explanation of the constitutive laws and weight savings, and how you apply those in a real car body. So shown here on the lower right is the body in white, or the primary structure, the body structure for a mid-2000s Mercedes C-Class. I've copied this out of a book published by Mercedes. Back in the day, Mercedes used to publish some very detailed technical books in Germany whenever they released a new car. And they would give lots of detail on all the different materials that they used and the different suspensions they used and information about the suspension geometry and how the car did in a crash, and they'd show examples and they go through all kinds of detailed things about aerodynamics. Apparently they don't do that anymore. I'm not sure why, but so this is for C-Class Mercedes. And the what I've done here, so just so you know, there are a couple of little pieces that are kind of cut out of this body structure for depiction purposes, so you can see more of what's going on. But there's a couple things missing. For example, the cowl right here. What I've done is I've taken this body structure, which looks very complicated, with lots of little bits and pieces and ribs and all kinds of places where you put bolts and things. It's really complicated, and I've sort of abstracted out the various beams and how they're loaded, and I'm showing that here. And I'll give you the names, the commonly used names for each of the beams. So here's a bigger version of what you just saw on the previous slide, and this includes pretty much all the main structural members that are in that previous slide, okay, that are in a car body, that are in this Mercedes C-Class. Starting at the front, we have the front bumper. We then have the rail structures. They go fore aft on the vehicle. They transfer load through a torsion box, shown here, to the rockers, which then transfer that load through another torsion box and up into these rear rail structures. And then there's a bumper in the back, a bumper beam in the back. When you get into a front impact, hopefully you never get into a front impact, but these cars are designed for, this structure here will be loaded. It will transfer that load to the crush cams, which then go into the front rails through the torsion box, through the rockers, and usually are kind of neutralized by the time you get to the rear of the vehicle. They also transfer that load into these inner rails here. So the objective a lot of times in getting an efficient structure for crash protection, for front-end crash protection in an automobile, is to have a nice smooth flow of stress from this beam all the way into these structures. So into these front rail, back through these inner beams, into the rocker panels, and then so this is done better in some cars than others, but this is the objective, though, is to have this nice smooth flow of stress energy or crash energy through this front of the vehicle. There are a variety of cross members that connect these different longitudinals. There are seat cross members, there's a rear seat cross member, there's sort of a tire tub cross member back here. There is an engine bay toe board member. As you go further up in the vehicle, there are these roof rail structures that you see here and here. These are attached to the rocker panels using what's called the B-pillar. So for those of you who may not already know the jargon, when you talk about, when you hear the term pillars on a car, the A-pillar, the B-pillar, the C-pillar, those are these pillars here. So this is the A-pillar. This would be sort of that structure that holds up the roof right in front of your kind of front to the front left of your body if you're sitting in the driver's seat. There's the B pillar, which is next to your shoulder, and then there's the C pillar, which would be next to the passenger in the rear seat. A lot of times there is a single beam that creates this roof rail, A pillar, and C pillar structure. Okay, a lot of times these are made from martensitic steels because they have to be really strong, because they take the load when the car goes into a rollover mode. And there's actually tests that the National Highway Traffic Safety Association requires, National Highway Traffic Safety Agency requires for rollover strength. And that a lot of that rollover load, if a car actually goes into a rollover, goes into these roof rails. A lot of times they're made of very high strength steels. The B pillar is oftentimes also made of high strength martensitic steels, because they take a lot of the load in side impact. What's not shown here is there's actually some members in the doors called door beams that take up a lot of the side impact loading, and a lot of the, or most of the load that's transferred from those side impact beams go into the B pillar, so it needs to be very strong. Um, the roof rails are held together using typically 3, sometimes 2, but usually 3 cross members: the front header, the rear header, and then the roof bow. The roof bow is oftentimes made of a high-strength martensitic steel because in a side impact it takes a lot of bending load. Okay. There are structural members that go sort of at the top of the rear seat that also connect the bottom of the C pillars. I should mention here that there are shock towers, like this one right here, kind of drawn schematically, at each of the 4 corners of the vehicle that take the loads from the springs. And a lot of times there's a lot of stress that goes into these guys because they're taking the main road input loads. And they're under a lot of fatigue loading, right? Because as you drive down the street, your car sees a lot of vibration. And these guys right here take up that fatigue loading. So these oftentimes need to be very strong. Okay, moving on to the next. There are a couple of, or family maybe of like 12 main loading conditions that an automotive manufacturer like a Chrysler or Ford or General Motors or Toyota uses to design that unit body, that primary structure of the vehicle with those different beams that I've shown you here. Static torsion or dynamic torsion, static bending or dynamic bending. These loads are mostly associated with how the vehicle feels when you go around a corner, so handling, and comfort, vibration from hitting bumps. The torsion load is almost like you took the car by the shock towers and twisted it. And the bending load is more like you held the shock towers fixed and then you put a beam across, let's say, the front seats and then push down on that beam. That would be a bending load. Torsion loading has more to do with the way the car reacts to steering inputs, so how it handles, whereas bending has more to do with, or impacts more the way the car feels when you hit a bump. Does it when you hit a bump, does it feel like it's nice and solid, or does it wiggle all over the place? So some other important loads that the body structure is designed for are front impact and rear impact. Okay, that's no surprise. And there's also side impact and rear impact, bending, torsion, front impact, side impact, rear impact. So here is a table where there are, on the very left here, there's a column with all of the different structural members that I've shown up here. And then there are 5 other columns for the different potential loading conditions on the overall body structure. So bending, torsion, front impact, rear impact, side impact. For each of the different structural members on the left, and each of these different sort of global loading conditions for the body structure, I've listed what loading these individual beams see. So whether it's C for compression, S for shear, B for bending, or T for torsion. In some cases, loading the vehicle produces multiple loading states on a given structural member. So sometimes you'll see here there's 2 letters under a given box. But I think the main takeaway from looking at this table is that you can now very readily look at these different structural members and begin to understand, well, if I make this part out of aluminum, for example, something that's in bending, then there's real opportunity there for weight savings. But if the part is really just only under tension, then I might as well make it out of steel because it's I can save weight with steel, right? I don't have to go to aluminum or something expensive like magnesium or titanium. So I would encourage you to look through this table and look at the different loading conditions for each of the different members and the resultant local loading to that particular structural member, and think about what material would make sense to make these parts from to get the most weight savings. And this is actually something that is understood in the automotive industry, and that's why there's a lot of talk about best light weighting at the best price through using a mixed material approach. So rather than making the whole body structure from steel or making the whole body structure from aluminum or carbon fiber, in some cases, it makes the most sense to get a lightweight structure that performs both in stiffness and strength and safety perspective by using mixed materials. I think a great example of that is the Audi TT. The current, I don't know if they still make it anymore, but the last generation, the last Audi TT that they made, very interestingly, they used steel. They used steel for these front rails and rockers and rear rails and B pillars, and then they used aluminum for things like a hood or a door or some of these cross members that didn't take that much loading in, that had more potential for weight savings and other loading conditions. So that is the end of my lecture for tonight. And if you have any questions, please feel free to email me at dbaskin@spectrummaterialseng.com. I believe you guys already have this email. I believe that Professor Eager put that address in the course syllabus. So with that, I'm going to say enjoy the lecture and have a good week at school. Bye.